As you can see, we have a lot of topics to address today. Let's see if it's possible. When Paulo invited me to come, I understood that it will be a course, introductory course about artificial neural networks. Now, 2 days ago, I understood that it will be a seminar. So let's convert all of this stuff into a seminar. Let's see if it's possible. So I'll make a very short introduction about artificial intelligence and the context of artificial neural network inside artificial neural networks. Then I'll move to artificial neural networks. I'll talk about the first artificial neural networks. I'll explain how it works. Then I'll talk about the learning, the machine learning, why and how the artificial neural networks learn. And in the middle, we have some questions. Also, I brought some books that are connected with the seminar, okay? That I will pass to you. Well, unfortunately, not to the attendees that are watching this session at home. Okay, so let's start. So the first thing to say is that artificial intelligence is a kind of paradox because it sounds to be fresh, and it is not a new subject. It's very old. Artificial intelligence has a birth date. So it born in 1956 in the first Dartmouth conference. And this term, artificial intelligence, was proposed by John McCarthy. John McCarthy was one of the pioneers of artificial intelligence. And so it was proposed, like I said, in 1956. In the first conference, we have a second conference 50 years later in Dartmouth with the commemoration of the 50 years of artificial intelligence as a computer science field. It is artificial intelligence. It is for the guys of computer science. It is a field of computer science. But I will argue that it's not the case. It's much more than a field of computer science, as artificial intelligence as transcendence. And what does it mean? It means it has a strong impact not only in computer science, but in the way we are living, the way we are interacting, and also in a way that we can think about ourselves. And that's the case of that you are doing a great job, in my opinion, because it's quite important to understand how this area can impact what we are and what we think we are. So that's the reason why it is so interesting, at least in my opinion, because it's multidisciplinary area. What is also interesting, you can see here, I read, is that the first artificial neural network born before the borning of artificial intelligence. So it was proposed by McCulloch Pitts, by these two guys, in 1943. So almost 80 years ago. So it's strange because, again, we are talking about artificial neural network and deep learning as being the oldest things of the world. It's so old, almost a century. Can we imagine that? Well, I will not waste my time, but I would say that if you are interested in history, well, artificial intelligence has a rich and very interesting history, full of hypes and full of, let's say, winters, if we can say this way. Anyway, I brought this book. If you are interested in the history of artificial intelligence, and not only, maybe you can consider to take a look to this book of Melanie Mitchell. Okay. Well, anyway, let's move because the time, like I said, will be. So as you can see, the story is rich. I just put some milestones here. One interesting milestone. It happened in the 70s that we call the AI winter. And why? Not because of the Lord of Thrones, but why? Because we have here a kind of frustration with artificial intelligence. And mostly this frustration came from the recognition that artificial neural networks were not so good as they were supposed to be. I'll return to this subject when I talk about the perceptron. But where we are today, as you can see, a lot of things happen. Another interesting milestone was the fact in 1997 that a big computer, Deep Blue from IBM, was able to defeat the world champion Garry Kasparov. And this was a milestone because somehow brought the idea that, okay, so artificial intelligence can beat the man. And it was something that till that time we were aware about this idea, but only in the fantastic literature. For instance, H.G. Wells, if you remember the 19th century. So suddenly it becomes real. Suddenly the computer, in this case Deep Blue from IBM, was able to defeat the man. Actually, by the way, it was minimax algorithm with alpha beta pruning. That is the old algorithm that was proposed by Morgenstern and John von Neumann. If you probably have heard about these guys. Many years ago, it was not related with this computer, it was related with economics. But today we are using different approach to play games against the humans. Anyway, let me move. I don't want to spend a lot of time here, I can't. But just to say that today, as you can see, a rich history of artificial intelligence. I'll not read this. Just to say that today we are in ChatGPT, in this case 3 and now 4, that is included in Bing by OpenAI. And we have a lot of challenge that exists in the Chat GPT. It's something that deserves to be discussed in this separated session. I will not address ChatGPT today, okay? But just to explain, ChatGPT don't know nothing about nothing, okay? This is just statistics, just to explain, right? But anyway, meanwhile, I put some links to some of my podcasts together with Microsoft, where if you are interested, if you have problems to fall asleep, maybe you can just click and then I can guarantee that you have a peaceful mind, okay? Just a second, right? Just in case. So here the book, if you want to know more about artificial intelligence. Why is so interesting? Artificial intelligence is really interesting. It is interesting because of many reasons. This idea that came from the fantastic, that can we have a machine? Are we machines like Descartes? If you think about Descartes, Descartes, well, are we machines? Our bones are mechanic, right? So is our brain a mechanic machine? Well, we know that it is not mechanic in the sense of having mechanisms, but in the other hand, yes, we have components and we have electrical inputs. Maybe it's fair to say that we are electric machines. Actually, we work in 17 kilovolts. By the way, I'll talk a little about neurobiology, just to explain how neurobiology has inspired these guys that I talked about in the beginning of artificial neural networks. But what is interesting to say is that, well, if you think about Arthur C. Clarke, the book Sentinel by the way, where the commemoration of his century 5 years ago, Sir Arthur C. Clarke, and the movie of Kubrick, 2001, A Space Odyssey, that in a way it was the translation of the romance The Sentinel of Arthur C. Clarke to movie. Maybe the most famous and most interesting movie that ever been, my subjective opinion, of course, maybe yours too, Paul, yeah, about artificial intelligence. If you remember Al and the ethical problems that Al brought in this movie. But as you can see, there are a lot of movies. Some of them are, let's say, really fantastic in the sense that they're crazy, like is the case of, for instance, Star Wars. That is kind of, well, this is for fun. There's nothing that is scientific in the movie. But some other movies can be seen as very interesting. Just to give some examples, this film, this is called Trashiness. For instance, is about the theory of Hebb. If you remember, right, the age of the book of Hebb, the age of spirit machines, the idea of connecting the brain with a computer and to transpose the thoughts and the knowledge from a computer to a machine. Another interesting movie that I asked all my students of artificial intelligence to watch the movie that I will recommend you if you have the time. It is Ex Machina. I don't know if you have watched Ex Machina. That is quite interesting about what can we expect from artificial intelligence that is what we call, or can be called, strong AI. Anyway, so everyone is interesting. So this is not just for scientists. This is just not for philosophers. This is for everyone, because everyone watches movies and everyone has the same questions. Even if you are not a philosopher, or if you aren't a scientist, you have concerns and you have interrogations about the future. And so artificial intelligence is able to fulfill this area. Well, what it is? Well, what is the goal of artificial intelligence? What are the scientific objectives? In a nutshell, we can say that artificial intelligence is about building and understanding intelligent entities. This is the scope of artificial intelligence. But what is quite interesting, and this is not, like I said, it's just a thing for computation. Actually, the computation here is just a tool. Okay? The computation is just a tool. So it's much more about philosophy, about maths, about psychology. By the way, some artificial neural networks, the first initial neural networks were proposed by psychologists. I'll talk about them in a minute. Okay? Okay. Some pathways to build artificial intelligence. We have at least 4 pathways to build artificial intelligence. So, how can we build this? And now we are talking about software engineering. How can we build? 4 different ways to build. The first, that is like the classical school or the symbolic approach, is about simulating the reasoning. This is the path of the cognitive psychology. So the brain is a black box, and the brain receives some inputs, and there comes several outputs. In the middle, there are a reasoning process that we assume that also incorporates existing knowledge that exists somewhere inside the brain. So, in this sense, the idea is to simulate the reasoning. So, this is the path of the psychology. Okay? It was the first thing. Here is not just associated with psychology, but also the logical, and in particular, one of the classic logics, that is the predictive logic, or if you prefer, first order logic. So the idea is to come from some assumptions, axioms, okay, and then to use some rules of logic inference to come out with knowledge. And this knowledge can be or not converted into actions. Okay? This is the first approach. Some systems exist. That was the first approach. Some language like Prolog, Lisp, actually Lisp was created by John McCarthy, by the way, follow this approach. Another approach is the path of the neuroscientists. So instead of having the brain as a black box. So you open the brain. And you open the brain, and what you find by opening the brain? So you find the hardware. Our hardware are neurons, as we know. Actually, we are not smart because of neurons. Okay? The neurons, by the way, are stupid. This, what was the idea? Okay, so let's take a look. Let's make an examination of the brain, and now let's replicate the brain. And that's the second pathway, the connectivist approach. So the idea is to have an inspiration in the nerve physiology to create artificial neural networks. So the artificial neural networks are inspired in the biological neural networks. We have some other systems that are inspired in connectivism, just to explain. For instance, immunological artificial systems are inspired on our immunological systems. And they are quite good. Okay, they are quite good. Third, the evolutionary approach. So if here I simulate the hardware, in the first I simulate the reasoning, in the third I simulate the evolution. So here, machine learning came not by the learning of the one element of the population, but is the learning came from the learning of the population through a Darwinist process. This is the evolutionary pathway. Okay. Here I will not talk about this today, but it's just let you know it's quite interesting. And it's completely inspired in genetic algorithms that are inspired in the genetic biological process. Okay. Finally, we have the ecological approach or biological approach that is where it fits for instance, the swarm. If you have heard about the swarm algorithms, and what we have here is that a set of simple, tiny behaviors, a set. If you have a lot of simple behaviors, then you can suddenly find a lot of intelligence. And for instance, in flies, okay, well, they can't fight against it, right? If you try to kill a fly, one of these noisy flies, well, they seem to be smart, and they are smaller. But things like why the birds are able to fly to the south in the winter and to return to the north in the summer. Well, do they have a GPS? How do they know? And this is related with this ecological approach. So it's just to highlight that we'll talk about this, but this is not artificial intelligence. This is a pathway to create intelligence. We have some other pathways, and better than that, we can mix this. Okay, you can have a system that is a mix of everything. Right? All right, this is what I want to talk about to contextualize the artificial neural networks. So in the minutes of time, oh, by the way, thanks to the attendees that are watching this seminar at home, feel free to interrupt me whenever you want, okay? I'm trying to move fast. So let me, like I said, neural computation is quite interesting because it's an inspiration that came from different areas. And now let me talk about a little about biology or neurobiology. The first thing to say is, I don't know if you're aware, but our DNA has 98.8% of similarity with the DNA of a chimpanzee. I don't know if you are aware about this, but it is what we have. The second thing, so this 1-2%, 1.2% of the DNA is different from the chimpanzee. And this small difference is not a small difference because it allows us to have at least 35 million difference from the chimpanzee. And why I'm talking about this? I'm talking about this because this open space for a philosopher from Oxford, probably no, better than me, defined as being super intelligent. Okay, and I'll talk about super intelligence in the middle of this. By the way, till 10 years ago, we believe that during our lives we don't have any new neurons in the brain. What is well, you say interesting. But in the last 10 years, some researchers found that there is neurogenesis in the brain, namely in the hippocampus area of the brain. But say that the born of these new neurons is not significant in terms of the number. So, well, we're not expecting to watch our head grow. Okay? Probably it won't happen. To be funny, because you can imagine if after you finish your master, then you have this side. After PhD, this side. Okay. Well, could be, but it is not. What is interesting in our brain, it is our ability to store information to learn, keeping the same neurons or less neurons that we have since we're born, because during our life, a lot of neurons just die. For instance, if you are drinking a beer, you for sure will kill some neurons. Okay, right? But we can say that's a kind of strange thing, because with the same hardware, we can accumulate knowledge and more knowledge and more knowledge and more knowledge. And this is the opposite of the computers, because if you want to store more information with this computer, then you need to extend the memory. Then how it's possible to, having the same hardware, to continue to accumulate knowledge and to learn things? That is quite interesting. And this is what I'll talk about in a minute. Here, the book that I've talked about, from Nick Bosman, just to say that three things very fast. Actually, I have your first question here, but I'll skip this question because I prepared some questions. Okay, but I'll prefer to postpone these questions to the end if we have time, as I'm really stressed with the time, as I told you. But just to explain, if you read this book, that I really recommend you to read, it's quite interesting. You'll see that, well, the first thing is, well, what happens if there is a being in the university that differs 98.8% of our DNA, but in this case, not for being less intelligent, but for being more intelligent. Okay, if so, probably we need to assume that in university there will be beings that are much more intelligent than humans, like we are more intelligent than the chimpanzee, just because having slight difference in the DNA. This is an idea that we can discuss if we believe that it's possible or not. The second idea, this is connected to the first, is can we change the configuration of our brain directly or indirectly to the generations to create better and higher biological cognition? Yes, no, this is the discussion. The second thing, that also from Oxford, the words of Sonberg, that's the whole brain, the WBE, whole brain emulation. What happens if I can build a machine that has exactly the same neurons that we have, but more resilient, or even if I can extend more? Can I emulate the brain in the machine, and that's how it will be more intelligent than the humans? And finally, the idea of artificial intelligence. And probably this is the topic that is more important to us. Can artificial intelligence be more intelligent than the man, than the human? Will we have such systems? And if so, what to do? Will we condemned to die? Will the machines kill us? What happens? And so, like I said, these things need to be discussed in the context. By the way, what happened? What happened? Everyone knows Stuart Russell, and this book is exactly about that. What happened if we build an artificial intelligence that is able to be more intelligent than the humans? Also, a book that is impossible not to read. Okay. All right. So, some facts. What happens if we can create a computer like that? We'll be able to be smarter and to solve all type of problems. And the thing is, it's completely false. Our brain has some problems. For instance, we can be confused. And what happens is that these artificial networks will be confused. You'll see an example because I brought a Perceptron to you. Actually, you can share my code with everyone. Anyway, and you can change the code. I brought a Perceptron just for fun to show how this is completely false. Anyway, so we should not be surprised that the neurons are not able to solve everything, but saying that, they are quite useful, and then can, as we are all aware, for instance, by trying ChatGPT, but not only because of ChatGPT, and even in small things, in the TV. So artificial intelligence, where is it? It's everywhere. Okay? Today we have artificial intelligence algorithm everywhere. Okay. Anyway, we are not smart because of the neurons. Actually, all neurons are stupid. They can be seen as balloons. They are called potassium and sodium pumps. So what is like a balloon? They are being filled not of air, like a balloon. They are being filling of sodium and potassium ions, and then they will just expel these ions, and then they will start. So it's a cycle of pumping. All right. So if the smartest is not in these balloons, where is the smartest? Well, the smartest is located in the relation of the neurons. So if you want to understand how we learn, well, now we learn by changing the influence of the neurons to the other neurons. And this influence is implemented with the synapse, in particular with the synapse networks. So if we want to understand how we are learning, we need to understand this mechanism. And is what was learned when the first artificial neural networks were created was exactly the replication, the mimetization of this mechanism. Okay. So our hardware, well, this another interesting thing is that our brain weights is 1,375 grams. The women weights is a little less, 1,275 grams, so less than 100 grams. But there are women that are smarter. The men we all know, if they are not, well, but at least there are a huge number of women. So it's not related with the size and the weight. Actually, if you compare the human weight with the elephant brain weight, you see that it's quite different. So it's not about the weight, because as I said, it is related with the influence of the neurons, the way all the neurons are influencing each other. Okay. So what we have, according to the latest studies, 86 billion neurons, maybe till 100 billion neurons. But today, if you read this most interesting, the latest papers, people tend to say that we have 86 billions. So it's not much. If you compare with the bits that are stored in the computer, or even in a smartphone, it's not much. What is interesting, what is important is the connectivity between these 86 billions. This Connectivity is partial connectivity. It means that not all the neurons are connected with all the other neurons, but is higher. So we have you can read this. This is what I'm just saying. Just explain some more things that this. So after the polarization, through the axon, we have action potential, okay, that is expelled, is a electric sign that is expelled through the axon to the end of the axon, to the synaptic button, and it will happen two things. The first, it will depolarize the sum of the axon that expel the action potential, and for the other hand, will polarize the dendrites. So it concentrates a lot of ions in the outside of the falling neurons, and it means that we have, like I said, a kind of network, sequential network. This potential action is, like I said, something like 70 millivolts. Okay, this is quite interesting in our brain because it never overcomes 70 millivolts. So you know, this is something that we watch in the cartoons, that someone thinking too much and then having fire and smoke in the head, right? It won't happen. Okay. Anyway, it's enough to turn on the lights.
I have a fast question. Will the all action potentials, will they arrive at the same time to
the falling networks?
Yeah,
the falling neurons?
yes.
Yes.
Somehow.
It's something that is not true in electrical circuits because we have the division of the power and the division of the flow. But in the brain and also in our models, we assume that we have no fan-out, like we have in the digital systems. So assume no fan-out. It means that what is fired, by the way, we have this, it takes 2 milliseconds. If you consider this period of time, that means that our speed is something like 500 hertz. Even if you are from English.
It's special.
It's 500 hertz for everyone. Okay. So we are not so fast. Okay. Just because, and even if we want, we can, because there is a refractory period here that the neuron needs to recover, to establish the balance between the neurons that are in the dendrite and that are inside. Okay. It's a kind of rest period of time, right? Okay. Well, like as you can see, we assume that what is fired by this neuron will be inserted directly in the dendrites of the others. Actually, it's the same in all in the special neural networks. Okay. What happens if you put more ions? Like I said, it will not overcome the 70 millivolts in terms of the peak of the potential, but you have more peaks. It's just one. The same in the special neural networks. Okay, will replicate exactly the same thing, right? This is something that I like very much this image, let's just explain. So here the buttons are here, okay? So here the efficiency is here. So this neuron is influencing is by adding this efficiency and this without efficiency. So the synaptic gap is where is the knowledge. Okay, let me skip all of this. All right, talk about this. Something interesting is that the metabolism of this sodium potassium pumping consume a lot of energy, and at least it consumes 20% of the energy of our full body. So if you are reading for a day or studying a subject for a day, you'll be tired, and you need to sleep to recover to allow your brain to recover, because it's really very demanding on terms of energy. We are not sure, but we assume that because of this reason of being very demanding in terms of consumption, that when we're born, some neurons are killed. Actually, they receive a kind of message to commit suicide, right? So suicide, and why? Why our body is reducing the number of neurons? Well, probably to decrease this energy demanding, but it's not sure. No one knows. Anyway, so we have this condemnation process, but also, like I said, it's something that is surprised. It's not clear explained yet, but we have a process of neurogenesis, is like I said, in the hippocampal area. So this is a brief overview of neurobiology, but well, let me be very clear. I just explained the basic of the basics, because our brain is not fully understood. And but okay, it was enough to create artificial neural networks. Actually, if you think about this pumping, it was kind of obvious for the scientists in the 40s. They looked at this pumping model and said, well, or it's full, or it's polarized, or it's no polarized. So is this polarized or polarized? So 0 or 1. So like Boolean logic, so like a flip-flop, if you know what I mean. Okay, so it's 0 or 1. So it's no surprise that the first model, McCulloch Pitts model, was a binary model. But thanks God, we are not binary. So the first model, neurocomputation model, was created in 1943, like I said, by these two gentlemen, McCulloch Pitts, was based on these things. By the way, this idea of ignoring the details is not so clear. And one of the reasons that some authors, and for instance, this neuroscientist that I got today, a book that I really think that's quite important with the new theory of intelligence, okay, that I really recommend it. Said, well, probably one thing that we have, one of the reasons why the artificial networks are so stupid is because we are ignoring too many details. But let's start with the 40s. What happened in the 40s? Two things. Okay, so we just have a neuron, and the neuron is connected with another, neuron 1 and neuron 2, with a wave. Okay? So if we have another neurons that are connected here, okay, then this neuron will integrate the flows, the contribution of these neurons, and we will make a decision of what will outcome. Actually, well, like in the biological, networks. Okay, so in a way, what to say? Well, if this influence is positive, then you have a positive weight. If it's negative inhibitory, then you have a negative weight, for instance. Okay? So, what we have in this model, and here you have the functional brain book that, like I said, another question. So if you want to have AI, can we have true AI before we understand the brain? Another question that I will not discuss now. I'll move a little faster. By the way, I will not read this, but I'll let this. I assume that these slides will be shared with everyone. Okay. So some of the things here, just for, but to explain that also the diffusion network has an history. Okay, an important history. And just explain they start in the 40s. I'm talking about McCulloch Pitts. Today, we have the SVMs in the 90s.
Sorry. Peter, you are saying that there are two maps there, the same.
No, what I'm saying is that when you have a model, the simplified model, all these things that I was talking about, the ions, the transmitters, neurotransmitters, neuroreceptors, okay, are ignored. We ignore this. So we ignore the details. So what we have in the end is something like this. It's just, well, if its influence is positive, we have a positive number. If it's negative, and what we have here you have a threshold. Okay, and if the threshold is reached, then the neuron will fire. If it's not reached, it will be quiet. Okay. So we have a history, as you can see, it starts in the 40s, so almost 80 years. I'll talk about the perceptron that came in the 50s. Then here, as Minsky and Piper wrote this book in 1969, and they killed the perceptron. It's a historical book. Okay, they were able to kill the perceptron, and they killed for almost a decade the area of artificial neural networks. Okay, all right. Today, as you can see, we are in the deep learning age. All right. Right. Anyway, is where we are. So let me talk about McCulloch Pitts formal neuron that was proposed in here. We have a photo of them. These guys. Well, now we look to this and we think this is ridiculous. How is it possible to propose so stupid thing? Take a look of this model. First, we don't have the same neuron cannot has different weights of inputs. Then, if it's negative, if we have such a negative, then it will be absolute. That we will put the neuron output can nothing. Second, it was just binary. So how it works. And I want to talk. So the inhibitory synapses were absolute. And let me give an example. So the inputs, as you can see here, were multiplied. So it is the input multiplying the weight plus the input multiplying the weight plus. If we reach the threshold, then it will fire 1. If not, then it will fire 0. This is a binary. Now we know that it's completely stupid because this approach indicates that they were fitting, that we were binary. So if so, then our neurons will be very stupid because we have 0 or 1 like a binary system. But at the time, knowing what they knew about the brain, it was acceptable. So let me give an example to explain what can be you represent. For instance, if you want to represent the ends, you can use this artificial network. This is a McCulloch Pitts neuron to represent this end function. If you put 0 here and 0, 0 multiplying 1 will be 0, plus 0 multiplying 1 will be 0, then 0 is less than 2. Okay, so the output will be 0. If we have, for instance, here A1 and B0, A1 multiplying 1, 1, 0 multiplying 1, 0, so 1 plus 0 will be 1, less than 2, so the output will be 0. And of course, you just have the 1 if you have both inputs, because it will be equal to 2, and then we do. By having this approach, you can represent the OR function, any Boolean function, and even functions, more complex functions. Here you have the short. Okay. Why? Because the short A short B. So you can represent any type of Boolean function, right? Just explain why this is what, okay? All right. So, anyway,
10 minutes.
okay. We'll just explain. No, tell me the money. No. Okay. But, okay. Well, is it anyway? So just explain. This neuron was all or nothing. So 0, 1. But what happened? Well, we are not 0 or nothing. And why are we intelligent? Because we are not binary, we are no logical. What does it mean? It means that the output of the neuron is not 0 or 1, but is a real number. And what can be stored in a real number? If you remember, I will not explain now, the Cantor numbers. I'm not sure if you are aware about Cantor numbers, but you can convert any number of bits into a real number. Okay. For instance, if you have this, it could be put as okay, and so on. Okay. Okay, just explain. You can have infinite bits converting a real number. Okay.
What's the difference between the McCulloch Pitts?
Oh, it's not binary. Actually, it's the more integrated file model that was proposed in the 70s by Bruce Knight is the model that we are using in deep learning. This is the current model. Okay. So what we have internal variable, U variable. I use ipsilon in inside the neuron. And this variable is integrated file because it's a two-step model. In the first model, there is integrates, like in the neuron, the biological neuron when he's simulating the flows of ions. We are integrating all the inputs in this internal variable. In the second moment, we are creating the potential action by using a function. In this case, the function that is common is the sigmoid function. So it's a but any continuous and monotonous, continuous and irreversible function can work. As usual, if we don't say nothing, we are using the sigmoid. Okay, and usually we don't discuss this sigmoid and sigmoid. Okay, so what to say? How it is? So in the first moment, we have this internal variable. Let's imagine that represents the polarization of the neuron is integrating all the symbols. The symbols is what it came from the dendrites, from the inputs of the neuron. After, if it reaches the threshold, then you fire. It will fire And what you find, it will depend on the inputs. Okay, so in a sense, what you have, if is the input, ipsilon again, like in the McCulloch Pitts, is the input multiplying the weight, input multiplying the weight, plus the bias. This bias exists for linear shifting. I will not discuss this now, but it is a good idea to use the bias to have linear shifting, special for decoupling from zero. Because zero, the use of zero in diffusion networks is not a good idea because it slows down the learning of the diffusion network. Okay. So this is a sigmoid. So what is output being output by the diffusion network? Not 0, 1, but will be a value that belongs to the sigmoid function. How many values can I have here? Infinite values. Okay. That's the reason why we can learn infinite things, because we can have more information. In the end, we'll just choose a real number. Okay. Right. So this is the current input. My last thing, as you can see, I will not talk about many things, but anyway, I'll just talk about the learning, how the artificial networks learn, and then I'll show a perceptron, okay, from 5,000 watts. Okay, I don't have, but as I said, if you are interested to organize a small meeting about this service, I'll be happy to show up and to talk about with more detail about all these things. Okay, so how they learn. Well, we just discussed if you remember when we talked about the biological, I talked about the neurobiology, not because nothing, but because all of this, all the diffusion networks are inspired in the biological networks. And if you remember, we discussed that, okay, our brain learns by changing the efficiency of the synapse, this concentration of ions. So learning means to change the weights. Or what is to learn? Is to change these values, the value of these values. Learn is to change the values of the values. Change the weights, like in the biological. So one of the first laws that appears was a Webb law. But by the way, we have several different algorithms. We have supervised learning, it means that we have a teacher, and supervised means that you are alone, and we have the means. Okay, that should be semi-supervised. Also, you can learn with your feedback. It's called reinforcement learning. Okay? It's the case of ChatGPT, reinforcement learning. It's very powerful. Okay. So, how can a system learn? Let's imagine that we have this association F and G. They have two vectors, and G is the answer to F. So, if I ask the system, what is the answer of F? If it's correct, you say G. Okay. All right. So let's see what. Don't know where. Oh, by the way, another question here. Just to explain, I'm talking about neural networks, but by the way, machine learning is not equal to artificial networks. There are some other types of, like I said, genetic algorithms are machine learning. Just to explain. Today we are talking about this. And by the way, a lot of people is so fresh and so trendy that people now are thinking, no, machine learning is artificial networks. It isn't. Okay, this is fine. All right. This is the reason why I put this here, just to recall us that it's not the same. So here we have the photo of Donald Webb. He was a psychologist, and what he said. Well, he said that we have a learning matrix. And what is the learning matrix? Let me explain here. This example. So what do we have? We have F, the F vector, that is input, and I have the G, that is the output. And here, the learning matrix is composed by all the weights. So the learning matrix are the weights of the neurons that belong to this neural network. Okay? So, if I want to get G, and this is from linear algebra, okay? From linear algebra, if I want to get G, I just need to give F, okay, to present this vector to the learning matrix, and then I'll calculate G by making this simple matrix multiplication, right? This is it. And this is ask. But if I want to teach this artificial network, so it means supervised learning, okay, that's what I'm talking about. It means that, okay, I want to define what is A, right? So what I want is, so A, let me write here teach, to be G, and F will move from this side to this side. I have the transpose function of it. Okay? So train, now return to this. Train is G, F transpose because of that reason. Okay? Right? So now let me see. An example. So I have these two vectors, and I have these two vectors, quite simple, and I want to teach this association F1, G1. So what to do? I will calculate the learning matrix 1. Okay? I'll not repeat this simple process. So here we have, and we got this learning matrix. And now let's see if this association was, this knowledge was memorized. If it was memorized, then you have this. Okay? So you present F1 and you are asking, and if it's correct, okay, fantastic. But I told you that we are training two vectors. What happens if I ask the answer to F2? If I ask, no answer. Why? Because the artificial network was not trained. No one taught this artificial network on this side. But can I add more knowledge? Can I train? And the answer is yes. So I can train. So I'll repeat the process. And I can train A2 on pattern association F2, D2. So the question is, okay, but what happened to the first learning? Will the artificial network be able to keep the things? And the answer is yes. That's good. Okay, yes. And this, once it's yes, then you just need to sum the learning matrix. If you sum the learning matrix, that is one block. Then this learning matrix will be able to answer. And this is the power of the artificial networks. Okay. Because you are able to ask, and here to train another example, I want to train the OR, the AND. So we have 4 learning matrix. And this learning matrix knows the 4 segments, okay? Even with patterns, if you want to and learn what is a triangle, or if you want to learn what is a triangle or a square, you can learn. So this artificial network is able to memorize a cat, a dog. It depends on the number of the size of the vector. Okay. However, okay. I will not explain this because I want, but we can easily convert this algorithm, this matrix multiplication, to a simple algorithm. This is the algorithm of the web learning. Okay, look at here. We are summing the old weights that belongs to the matrix in order to keep the existing learning. Okay, but what happened? These artificial neural networks are single layers. Okay, single layers, right? And what happened is that after a while, they start to forget. If you are teaching a lot of things, they start to forget what they learned. Even adding. So what happened in the end of the 60s is that people become disappointed. Because single layer networks, even these ones, Adaline or Hydro is the same thing, even the Perceptron, where after a while they were not able to keep the previous knowledge. That fact was just solved by in the 80s by the words of Santos group, Multilayered and the other guys. I will not talk, obviously I will have no time to talk about this today. When we were able to generalize Adaline to the break propagation algorithm. And today we have multi-layer algorithms, deep learning is the case, and they can memorize everything. Everything. When I mean everything, it's everything. Right? So I'll just talk about to end this seminar. I'll just talk about Frank Rosenblatt. Here he is to end. And the Perceptron. Here he is the guy. He was a psychologist like Donald Webb. He was responsible for the best. I brought a very important book. As you see, it's so important that there's some parts that has handwritings. Okay, it's the book of Marvin Minsky and Sigmund Peppers. Okay, historical book. Why Frank Rosenblatt is why he is a very important character in the artificial neural networks, because he was responsible for everything. He was responsible for the good, for the best, and for the worst. He was responsible because he was in charge of creating a huge enthusiasm around artificial neural networks with his perception. Because he states that he and his engineers, he said that perception could do everything. And actually, he was responsible for the winter because in this book that João is holding, in this book, Marvin Minsky and Sigmund Peppers was able to demonstrate that the perception has a lot of problems. Okay, now you want to watch a perception work? So the machine. Okay, just to explain. Let me show you just to end, just to show you a perceptron. Okay, this is a perceptron. Let's see if it's working. Oh, it's protected. I can anyway.
Okay.
But anyway, I'll be happy to share with you.
Let's do some Q&A.
Okay, go ahead.
So have we some feedback?